This video will discuss spherical mirrors and how they bend light. A spherical mirror has the shape of a section of a sphere. If the outside is mirrored, it's called convex. If the inside is mirrored, it's called concave. Spherical mirrors have a central axis, a radius of the sphere, and a center of curvature, the center of the sphere. So the center of the curvature would be the center of the sphere, and the distance to that between C and the mirror is R, the radius of the sphere. So imagine light hitting the outside surface of the sphere. Remember, this is called a convex mirror. When light hits it, due to the angle of reflection, light coming in parallel will bounce off at an angle away from the center of the sphere. Notice that all the refracted rays are bending away from each other. So the real light on the side of the mirror that the light is hitting, reflects off and never ever intersects with each other. That tells me that since these rays will never intersect, that this mirror will always make it a virtual image. I can dot back those refracted rays, and I can see that they do all converge on a single point, and that point is half of the radius of curvature, or the focal point. So by definition, a convex mirror diverges light away from the focal point of the spherical mirror. And remember that the focal point is always half the radius of the curvature. If instead the mirror is on the inside of the sphere, we call this a concave mirror. Easy for me to remember because it looks like the inside of a cave. When light parallel to the axis comes in, it will be bent downward and will refract onto that common point, the focal point. So by definition, a concave mirror reflects light such that it converges the rays onto a common focal point. And remember that focal point F is at a location half the distance of the radius of curvature. So a convex mirror, because it's focusing on the inside of the mirror, has a negative, let me go back. So that convex mirror, right, that never really focuses light on a real point. It's projections focal that always that diverges light, in other words, and always creates a virtual image. The focal length is said to be a negative focal length. So by definition, convex mirrors, because they diverge light, have a negative focal length, which is half the radius of curvature. A concave mirror that's mirrored on the inside, like the inside of a spoon, will have a positive focal length because it converges light onto the focal point. And once again, the focal point is always half the radius of curvature. So remember that that spherical mirrors do have a problem with the fact that light doesn't always converge on the same focal point, depending on the color of light. So spherical mirrors are not perfect. You can only have a spherical mirror that's only so big. The bigger the mirror, the more likely it'll have a spherical aberration, which just means that light isn't focusing all on the same point like it's supposed to. So to correct that, you can make a mirror a parabolic mirror. So in other words, taking it out of a sphere, you can correct that spherical aberration by cutting the mirror out of a parabolic shape. And this is what's used in really big mirrors, like for instance in telescopes. The Hubble Space Telescope had spherical aberration because the mirror in it was too spherical, and it didn't have enough parabolic shape to it to correct for that. So therefore the pictures were blurry and it didn't make very good pictures, and that had to be fixed. And so it was very, very costly. The main reason it occurred is that when they designed the mirror and designed the shape of the mirror, they really didn't calculate the conversion factors that they needed from English units to metric units. And so they actually made the mirror too spherical because they didn't use the proper conversion. And that was a multi-million-dollar mistake that had to be fixed, which was very bad for NASA.